Hey guys, so I'm actually right now at the Technion Labs with my friend Steven, the one I did the song with. This is his laboratory, and this is where he studies yeast and enzymes. And today, you shall show us around your lab, correct?
Yes.
Sweet. Alright, so what's the first thing you want to show us?
Let's start from one end of the lab.
Alright.
Okay.
Hold on, first maybe we should describe that these windows are not like a bunch of seagulls that crapped all over it. It's like construction right now, right?
Yeah. So they noticed that there were lots of cracks in the building, and they decided to do something about it. So they're just scraping the places where it's cracked and just putting more cement in there and making it nicer. And we're in the middle of the process, and that's why it's like this.
Yeah, when I first saw it, I thought it was a bunch of like bird crap that just, I don't know, somehow got on the window over time that no one decided to clean. Anyway, let's get back to your lab. So where are we starting?
Well, like any typical lab, we have desk spaces where people actually do their work, and this is a typical desk. So we have pipette stands where we have pipettes of different sizes to take different volumes of samples.
And how accurate are these pipettes?
They're pretty accurate. You can look at this. This takes about 0.2 microliters of a sample.
Okay.
That's pretty accurate. And the maximum that we have is 1 milliliters, 1 ml. And if we want to take volumes of more than 1 ml, we have other pipettes to do so.
Oh, sweet.
Well, other than that, we have tips to take solutions
fresh,
from.
Clean tips
of different sizes. Of course, we use certain solutions regularly, and so we prepare them in advance and keep them on our desks. And that's it. So our lab, we work with yeasts, okay? And we've chosen this yeast as the model organism to study to answer our research questions because it's a suitable model organism to get answers for our questions. So our main question is to study how genes regulate themselves, how gene expression is regulated. So gene expression is the fancy term for the transfer of information from DNA to RNA and ending in protein. So that's how we're built. It's this mechanism that primarily builds up a human being, or
it's instructions, right? Just simple as terms, it's instructions, right?
Yes, or a living system in general. So to do so, we work with yeasts, as I mentioned, and so we need to grow them, right? So they need food to eat, water to drink. So if you will come over here, I will show you. We have what we call the culture media, okay? Can you see these bottles here? And we have solutions in them, right? Of course, we've given them names. You can see the abbreviated names of those.
Yes.
So these are basically food and water for those yeasts.
Are they like different combinations of water and food as well? Probably
yes,
sugars
they're
and
different
stuff?
combinations. So we grow different kinds of yeasts for our purposes. And so each of these media that you see here will allow the growth of a specific kind of yeast.
Okay.
So, for example, this is a media made from yeast extract, peptone, and dextrose, which is why it has the name YPD.
Okay.
Okay, and here this is called minus TRP, meaning that this is the same media, but it does not have the tryptophan amino acids.
Okay.
Similarly, we have different kinds of different combinations of culture media which lets us grow the specific yeasts that we want to grow. So that's about the culture media.
And people that don't know what do you call this again?
Minus TRP.
Minus TRP. If you don't know what that is, just know in biology class that mitochondria is the powerhouse of the cell.
Well, what you just said is true, but it's not connected to this.
Yes, I know. I'm just saying, people are probably not going to know exactly what minus TRP is. So all you have to know is about biology is mitochondria is the powerhouse of the cell.
All right.
Right?
So
maximum biology, right?
minimum biology. Okay, so
all right,
what do we have next? We can take a look at these things. All right, so this, for example, is a filter setup. Okay, what does it help us to do? We prepare these solutions, different, combination of different solutions, and we want to keep them clean, right? When we use them for our experiments, we want them to be clean, sterile, and non-contaminated. And so we can either pass them through extreme heat for a long time and thereby sterilize them, or we could mechanically sterilize them. And this, what you see here, a filter system, is one such setup to help us to do that. So we basically we pour the solution on this top chamber and connect this to the vacuum so that when we turn on the vacuum, it would suck the liquid from the top. And we have a membrane at the bottom here, and therefore all the contaminants, the fibers, or whatever, the contaminants, yes, that will be removed, and you will get the pure liquid at the bottom. So this is just one way to sterilize the liquids that we use.
Sweet.
Yeah, and so very often we work in different temperatures. Okay, certain solutions cannot be kept at 24 degrees, which is the room temperature, and they need to be kept at higher temperatures, for example 37 degrees Celsius, right? And only then they would be active. So we have what we call heating blocks. This for example is a heating block, and you can look here, the temperature is 37, so it's always set at 37, and yeah, it helps us bring the solution back to that temperature where it works best.
Okay.
All right, and what we have here is a very tiny but very useful piece of machine. It's called the Vortex Machine. What it does is
Vortex Genie too.
Yes, that's specifically the brand. But what it does is very simple. It helps to mix the sample in your tube really well.
Okay.
I can show you let's see how it mixes. If you will be patient with me, I can show you. Okay. This is a 1.5 ml tube that I have here. And let's say I want to mix the solution really, really well. So what do? I go put it on top of this, hold it tight.
Oh, wow.
And then turn it on. That's it.
It's pretty cool.
Yeah. It's very simple though. So this is one very handy piece of machine. And let's get to this. This is another very simple machine that we regularly use, and it's called the centrifuge. And the goal of the centrifuge is to separate the materials that are in our solution. Okay, the way it does is it runs in high speeds, and because of the centripetal force, the higher weight particles will settle at the bottom, while the less heavy particles will settle at the top, and thereby we could separate different materials in our solution. So that's it.
It's a very useful tool.
Yeah, it is true. And you see these? You see a lot of these around, okay? These are called ice buckets. And right now there's just water in here, but as I told you, a lot of experiments that we do needs to be at certain temperatures. And we talked about using a higher temperature. But very often we need to keep the samples at lower temperature, and preferably at 4 degrees Celsius, because that's the temperature at which not much biological reactions happen. And therefore, when we work with it, they're not active. And so we can manipulate stuff without losing an activity, for example. And so we need to work at 4 degrees Celsius. But how can we do it? So what we do is just take some ice. I will later show you where we take ice from. We take some ice, put it in this bucket, and carry it around, keep our samples here, and do our experiments.
Now, how do you know it's regulated at a constant 4 degrees Celsius?
Well, it is, as you know, ice has a temperature, sub-zero temperature. Not necessarily sub-zero, but 0 to 5, for example. Mm-hmm. So that's sufficient. What I would like to show you next is here. Well, if you're familiar with chemistry, this is
Erlenmeyer flasks, right?
Yes, exactly.
And the graduated cylinders.
Yes.
Nice.
So,
I know my chemistry, man.
You do? Yeah, I'm not surprised. You went to a good school, okay? All right, so I'm going to show you something else.
Hold on. Look at this thing. What is this, 200 milliliter Erlenmeyer flask? This thing's
is
huge.
2 liters.
Yeah.
Of media.
Sorry, not milliliter. Yeah, milliliter. Yeah, 2,000 milliliters. Sorry, that's what I meant to say. Not 200.
Yeah. So, what we can show you next is going on the same line of temperature. I told you that certain reactions happen when they're too cold, when they're at room temperature, at really hot.
Wow.
So, in order to increase the temperature dramatically, fast, we use what we call a heating bath, which is basically a container with water, but it has a thermostat in this container, and we can regulate the temperature that's here. For example, if you look at this, it says it's 7 degrees. Okay? So that means right now the temperature of the water inside is 7, which is really, really low. But we can, if you look at the regulator here, you can increase the temperature to 75 degrees Celsius. And so there are experiments that we do in our lab that requires 70 degrees for like half an hour or so. So we make use of this.
Oh, wow.
Yeah.
Do you want it to still be on?
We can turn it off.
Okay.
All right, and here, these are all three, what you see here, are centrifuges, but they just for capacity, different capacities.
18,000 revolutions per minute or something?
No, the working limit is 14,000.
Okay.
Yeah, 14,000 revolutions per minute. And this also can go to 14,000, but the capacity is, the maximum capacity in a single tube that we can use here is 1.5 milliliters. Whereas in this, in this, I can put a maximum of 50 milliliters.
Nice.
And the advantage of these both is that they work even at 4 degrees Celsius, where the samples are still kept not active, and that's an asset for a biologist. So what we would move on from here. We would go to this place. Okay, this is a laminar airflow hood. Okay, yes, that's a hood. And what the purpose of this piece of machine is that if you can look above, through this place you get air and clean air. And so the idea is that this is a workspace where I can work without the contamination from the atmosphere, from the air outside. How? Because the air from above, which is pure, kind of pushes away the contaminated or the dirty air that's in here. And therefore, as I keep working, as this keeps working, I get to work in a sterile environment.
Oh, that makes sense. Very crucial, I would assume, as well.
It is. And what you see here, or let me open one for you. So these are basically culture plates. So it's basically food. So we grow the yeasts on these plates, and they have different colors because, as I told you earlier, different culture media have different components to them, and therefore they have different colors.
So this one is more of a darker color compared to this one.
Compared to this one, yes.
More of a darker yellow it looks, and this one's even darker yellow color.
That is true because it has some more stuff in it.
Okay.
All right. So then we come to an important part. You know, we do all these experiments day and night, and but you know, what if I say I work for like 3 weeks and purify an enzyme, and then I want to use it for a year. Like I want to use it today, and I want to use it for another experiment, which I will be doing after a year, for example. I need to store these things, right? I keep the protein. I purify it, but I need to store them. How do I store them? Store them. In other words, how do I keep them inactive for so long, right? So one of the ways we can do it is keep them refrigerated. Okay, I can refrigerate them at 4 degrees or at minus 20 degrees Celsius or minus 70 degrees Celsius also. And this is a refrigerator which maintains 4 degrees Celsius.
Oh, nice.
So you can see all these plates. So what you see inside are basically yeasts, and these yeasts have been grown on these culture plates, and we've used them for now, and then we want to store them. And so when I keep these yeasts at 4 degrees Celsius, it's good to be stored for like a month.
Oh, wow.
So yeah.
And obviously, do not put your food in here. This is not for food.
Not for food, yes.
Yes.
You don't want to be eating stuff that will kill you, right?
Yeah.
I can show you some stuff that will kill you.
No, keep that to yourself, please. I feel like living.
Yeah, you feel like living? But maybe they want to know. This is called TEMED, which is tetramethylethylene. As you can see, the warning symbol right here.
Yeah.
Yeah, that means it's harmful. Okay?
What happens if you ingest this or touch it or what?
If this goes into your system, into your body, you're dead.
You're dead?
You're dead.
Oh, wow.
There are a few chemicals that we have that if you eat them, if it gets into your blood circulation, you're dead. Which is why we use gloves when we work.
Fun.
And other protective measures. Finally, not finally, but we come to an important part, which is this is a balloon containing liquid nitrogen, people. Liquid nitrogen. So liquid nitrogen helps us, because of its extreme low temperature, it helps flash freeze your samples. Let's say I have a cell that I'm working with and I give it a kind of treatment and I want it to remain being treated that way. So as soon as I treat it and I instantly dip it in liquid nitrogen, it would flash freeze. And that means its metabolism would stop right away. And that helps me because it would help maintain being that treated state until I take it away from that state. So that's the advantage of having liquid nitrogen. And we can have a sample of how liquid nitrogen looks. Alright, let's have a look at the liquid nitrogen. So this is the hose that brings in the nitrogen. So I'm going to turn the knob on.
That kind of scared me at first.
Yep, because of the pressure. Can you see it falling? Yeah, there you see it.
It's pretty cool.
Yeah. Alright, so we're going to stop right there. It's like any liquid.
It's crazy to think of a gas being put into liquid form.
Exactly.
Okay, so you have some things we can test in the liquid nitrogen?
Yeah, just being a bit naughty. Let's see how a glove would fare in the liquid nitrogen, okay?
Let's see if it will like fracture or something, or
yeah.
After you place it on the ground or something.
Wow. It's
Well, and put it on the ground, maybe like step on it. Look at this. It oh, I don't want to touch. Should I touch it?
Yeah, you can touch it.
Look at this. It crumbled the glove into pieces. It was so cold that it fractured. Look at all these small pieces here. That's crazy. Okay, what's the next thing? We'll pick that up later.
The next thing is a piece of paper.
Okay, let's see if a piece of paper will freeze and crumble. So how cold is this right now, the liquid nitrogen?
I don't know the exact temperature, but I think it's possibly around minus 200 degrees Celsius.
Oh, wow.
Minus 200.
That's crazy.
Okay.
And that's Celsius.
And that's Celsius. Okay. I don't want to touch this with my hands. No, it's too crazy to touch it with my hands.
Here, I'll grab it. I'm kidding. You think I'm that stupid? Oh, you grabbed it. Okay, do you think I should touch it now? Let's see. Oh no, the paper.
The paper is...
It didn't do much.
It didn't do much.
I don't think it might have been sitting directly in it that well.
But we can see what a tube what effect it has on a tube.
So this is actually what you do. We were having fun before,
Yeah.
but this is what you actually do.
This is what we actually do.
Okay.
So we put the sample in the tube
Okay.
and stick it into the liquid nitrogen.
Easy enough.
Yep. And nothing happens to the tube. We take it and store it where we want to store it. That's it.
Cool.
Yeah.
Having fun with liquid nitrogen. Well,
Yeah.
conducting science.
Conducting science.
Join us next week, people, when we see Steven stick his hand in liquid nitrogen.
I'm not doing that. I want to live.
Yes. But man, look how professional he looks in his lab coat.
Well,
Just like a proper scientist. I'm
I'm
so
not-
proud of you, Steven. I'm proud.
thank you.
Your parents
That's
would be
an honor.
proud too.
I know they are. They've told me.
Pretty cool. Alright, well thanks for showing us around your lab.
You're welcome.
Alright, and see ya. The Casey and I side wave.